So now we're going to talk about how we can characterize the power that's delivered in an AC system. So just as with DC circuits, due to the conservation of energy, we can say that the instantaneous power, the amount of power that is delivered to an element or absorbed by an energy storage element within a circuit, is the product of the instantaneous current and the voltage. So at any given point in time, we can multiply the current through the element by the voltage across the element to determine the power. And the power here is in watts. That is representative of the amount of power that is absorbed by the element or combination of elements at any instant in time. The next thing I'm going to do is I'm going to represent my AC current and my AC voltage in terms of the trigonometric functions as a cosine. So this is going to be consistent with our phasor representation. We want to represent our current and our voltage as cosine functions. Also note here that I am specifying the amplitude in terms of the peak amplitude or the maximum amplitude. I'm not using RMS or effective values right now. So taking my two elements, my voltage and my current, for any element within the circuit, I can determine the instantaneous power that's absorbed or dissipated by the element. And if it's an energy storage element, we know that there's going to be a difference in the phase between the voltage and the current because the impedance of energy storage elements introduces a phase shift between the current and the voltage. Doing this, if I can figure out what the instantaneous current and the instantaneous voltage is, I can multiply the two of them together in the time domain, and I wind up with this function, which is the product of the current and the voltage that describes the instantaneous power. Now what I'm going to do is use a trig identity to try to simplify this, this expression. So I'm going to use my product of two cosine waves trig identity. And it doesn't seem like I'm simplifying this, but it will come back to hopefully show that, we will show that this leads us to some interesting results. So by applying this trigonometric identity to the product of the current and the voltage, we get two terms that pop out of our instantaneous power equation. We get one term, which is a constant term that does not depend upon time. So here we have the maximum voltage and the maximum current multiplied by 1/2 times the phase angle difference between the voltage and the current through the element. This one does not have any time dependence on it, so this is just a constant with time. So my first term is a constant, and my second term over here is looks very similar, but it is a function of time. The interesting piece that we see here is that this function of time, this instantaneous power, is going to be a sinusoidal function, but now it's going to oscillate at twice the frequency of the inputs. So our current and our voltage from our study of AC analysis or periodic steady state analysis, we know that when we force a function with a periodic input, the current and the voltage is going to remain the same frequency throughout the system. It's only the amplitude and the phase that's going to change. Here we see that the power is going to occur as a sinusoid at twice the frequency of the current and the voltage. All right, so the big takeaway here is that instantaneous power is comprised of this constant term and this time varying term at twice the input frequency. Now I'm going to apply yet another trig identity to that second term. All right, and again, it seems like we're complicating matters here, but another interesting thing happens. If I apply this, this trigonometric function, I still have my first term, which is a constant function of time, and then I have these two additional terms here. But what I see is that this first term that comes out of this trigonometric expansion looks identical to the coefficient of this cosine term right here looks identical to the constant term right here. And then I have a different constant multiplied by a periodic function for my instantaneous power. So what we do with this information is we rewrite this as a constant plus that same constant multiplied by a cosine function minus a different constant, q, multiplied by that sine function that occurs at twice the input frequency. And we define these constant terms. P is defined as the average power or the real power, and the average power or the real power is given by the product of the peak voltage and the peak current multiplied by 1/2, and also multiplied by the cosine of the angle, the phase angle difference between the voltage and the current. And we call Q the reactive power, which looks very similar, except it is going to be the sine of the phase angle difference between the current and the voltage through the element. Now, great, what does that mean? Well, these have some physical meaning to them. So that average power term tells us about the average of the instantaneous power that's delivered to the circuit over one period of oscillation. So what that really means is that this is the real power that is dissipated by an element, and it describes the rate at which energy is transformed from electrical energy to some non-electrical form. So this is how energy is transferred from electricity into heat, into a force, into a sound, into some other non-electrical form of energy. And we measure the average power in units of watts. Reactive power, on the other hand, describes the amount of power in a circuit or the rate at which energy is not transformed or is stored within elements of the circuit. Both real and reactive power carry the same dimensions. They're both the product of current and voltage. And so they can be conceived as being watts. But to distinguish between the amount or the rate at which energy is dissipated and the rate at which energy is stored, that is the real power and the reactive power within a system, we give them different units. So real power is expressed in watts, and reactive power, or the rate at which energy is stored within elements of the system, is given units of the volt-amp reactive, or VAR. The difference between the phases of the voltage and the current through an element is called the power factor angle. And the cosine of this angle is called the power factor. And the power factor is going to become important because it tells us about the efficiency with which power is delivered in a system. But this power factor alone is not sufficient to determine the phase angle. So we know that if the current and voltage are in phase with each other, we have a completely resistive system, and the power factor is going to be identically 1. Now, if we have an inductive load, we know that there's going to be a difference in how the voltage changes relative to the current through the inductor. Now, in an inductive load, the phase angle for the voltage is going to be greater than the phase angle for the current. So if we know what the power factor is, and we know that it's a lagging power factor, we know that the system behaves as though it were an inductor. If the opposite is true, that is, the current phase angle is greater than the voltage phase angle, we have a capacitive load. And there are two different mnemonics that can be used to help you remember this. The first one is the civil mnemonic. All right, so for the civil mnemonic, we take the first part, the CIV. C represents capacitor, I represents current, and V represents voltage. And that tells us that for a capacitor, the phase angle of the current leads or is greater than the phase angle for the voltage. So for a capacitor, current leads the voltage. And we take the last three letters of civil, and we use that to represent the inductor. So what this represents is the voltage phase angle leads the current phase angle for an inductor. The voltage leads the current for an inductor. So this tells us the current, so for a capacitor, the current leads the voltage. For a phase angle difference where the voltage is a greater phase angle than the current, we have an inductor. The other mnemonic is Eli the Iceman. So this comes from the fact that a common representation for voltage is electromotive force, or EMF. So E represents voltage. So again, Eli tells us that the L stands for the inductive element. So current voltage E leads or comes before the current phase angle for an inductor, and for a capacitor, the current comes before the voltage, or the current leads the voltage for a capacitive element. Okay, so again, repeating, a lagging power factor indicates an inductive load, and a leading power factor indicates a capacitive load. Now, the effective, the power, those power terms can be calculated using the amplitude, or the peak periodic voltage and the peak periodic current amplitudes, but it's often more convenient to express these in terms of the effective or RMS values. And as we what I've talked about before is that the effective value of a periodic current or voltage is going to be the same value, or the value of a DC current or voltage that would deliver the same amount of average power to a resistor. All right, so we've already calculated or shown how to calculate the relationship between the RMS value and the peak amplitude of a voltage or a current function. So knowing that the average or real power can be computed as 1/2 of the peak voltage multiplied by the peak current, or the maximum amplitudes, and the product of the cosine of the phase angle difference, or the power factor, we can rewrite this in terms of the root mean squared values of voltage and current. So we know that from the previous video that the RMS value is related to the peak value by the square root of 2. So if I substitute those in, I see that the 2 square root of 2 terms are going to turn into a value of 2, which is going to cancel this 1/2, leaving me with the following relationship, that the instantaneous power, or the real power term, is going to be computed using, not the instantaneous, the real power term, P, is going to be computed just as the product of the RMS voltage and the RMS current. Similarly, we can compute the reactive power in terms of the voltage, the RMS voltage, and the RMS current multiplied by the sine of the phase angle difference. So again, we can compute these terms using, we can compute the real power term and the reactive power term using RMS values instead of maximum amplitude values. So far, we've talked about 2 different types of components of the instantaneous power, the average power and the reactive power. There's another type of power we can envision, because the power is going to be a sinusoid function. We can define something called the complex power. Now, the complex power, remember that complex numbers, thanks to Euler's relationships, we can represent sinusoid functions as complex vectors. And the complex power term is the sum of the real and the reactive power as a complex vector. So you can probably see where we're going with this. We can use complex relationships to tell us about the power that occurs within a system using our using our Phasor representations. So the complex power is the real power part plus the imaginary number multiplied by the reactive power. So again, the real part is real power. The imaginary component is the reactive power. And again, both of those terms have the same dimensions, but we call real power watts. We call the reactive power volt-amps reactive, or VARs. And to distinguish complex power from real power and from the reactive power, we give complex power yet another unit. All right, and we call complex power volt-amps. We give them the units of volt-amps instead of watts and VARs. This allows us, representing the complex power in vector form, this allows us to easily compute the power that's dissipated by an element in phasor form. So in phasor form, we can determine the phasor or the complex power by taking 1/2 of the product of the phasor representation of the voltage through the element, across the element, multiplied by the complex conjugate, that's what this star or asterisk means, of the current through the element. Or using root mean squared values, we can take the product of the voltage and the complex conjugate of the current using the RMS value. What this translates to, of course, in terms of the amplitudes, is we can look at the peak magnitude of the voltage and the peak magnitude of the current and multiply that by 1/2 and take the phase angle difference for the angular difference, or we can use the RMS values. So if we can figure out the phasor representation of the voltage and the phasor representation of the current through an element, we can also determine the complex power of the element. That's either, and which in turn tells us about the rate of energy storage or energy dissipation within the element. This complex power may also be expressed in terms of complex impedance within the circuit. So again, we know that impedance is represented as a complex vector, and it's related to the relationship between the voltage and the current. Now this could be replaced by RMS voltage, or it could be replaced, or we could use the peak voltage or the maximum voltage as well. But I'm going to express it in terms of the root mean square value. So the complex power is also the root mean squared value of the current squared multiplied by the impedance. When we square the root mean squared current, we assume that the phase angle is 0 after we square it, so we don't worry about the phase angle there. Same thing for, we can use something similar to our Ohm's law relationship and come up with the fact that the complex power is the root mean squared voltage squared amplitude divided by the complex conjugate of the impedance across the element or elements that we're looking at, which again is the same thing as the product of the current and the voltage phasor. So now what I'm going to do is take a look at how all of this comes together. In this Excel spreadsheet right here, I have 2 plots, and those plots are tied to calculations that I'm going to be showing you in just a minute. Or actually, all of the calculations that have been shown previously for the instantaneous power. So we have a representation on the left-hand side of voltage, which is the blue line, and current through an element, which is the red line. Right now, both the voltage and the current are in phase with each other, so there's no phase shift between the two of them, which means that we have a purely resistive circuit. And when we look over on the right-hand side, this is a representation of the instantaneous power that's delivered to the element. We see that the power delivered across the element is occurring at twice the frequency of the voltage input, which is what we predicted, or which is what we came up with from applying the trigonometric identities to the instantaneous power relation. Now what I'm going to do is I'm going to change the phase angle difference between the voltage and the current. And I'm going to increase the phase shift for the voltage. I'm going to set it to 90 degrees. And based on our relationships, we know that for an inductor, the voltage, when the phase shift on the voltage is greater than the phase shift for the current, or that is the voltage leads the current, we have an inductive system. And because of the phase shift is 90 degrees, this is all purely an inductive element. And through an inductive element, through a purely inductive circuit, we see that the voltage and current are out of phase with each other by 90 degrees, and the product of the current and the voltage, which occurs at twice the frequency, we see that there was a shift in where this wave was located. So let me go back to 0 degrees phase shift for a purely resistive system. And we see that there's an average value here for the arbitrary numbers that I have it's about 6,000 right here. So that's the average value of power over this period that is dissipated by the element. And then when I change it to an inductor, we see that the average value decreases to 0. And this decrease to 0 indicates that on average, the amount or the rate at which energy is stored in the inductor is equal to the rate at which energy is being released by the inductor. So the real power tells us again that the average of this power, on average, the inductor is not dissipating any energy. It's only storing energy. And that's not completely true, because it stores energy at a particular rate and then dissipates energy at a particular rate due to the sinusoidal nature. But on average, it doesn't dissipate any energy. Of course, we can do the same for a capacitor. If I change the phase angle to -90 degrees, we see that the average power is still 0. Of course, in a real system that has inductors, capacitors, and resistors in it, there's going to be some voltage phase shift relative to the current phase. That is not going to be 0 or 90. It's going to be somewhere in between, and that is the power factor. And when that happens, we get some average value, some average power value that is below the maximum value when the circuit is purely resistive. And we see that when the instantaneous power drops below 0, this is the instant in time where energy is being stored within the system. And then above 0 is when energy is the period of time where energy is being dissipated or released by the circuit. All of this leads us to a final definition of yet another definition of power, which is called the apparent power. And the apparent power is the product of the effective voltage and the effective current magnitude of complex power. So basically what we're going to do is we're going to take the real power term and the reactive power term, square them, and take the square root, and that gives us a scalar value. This is in watts, and the apparent power it represents the amount of power that is required to supply the average power that we're seeing that's being dissipated by an element within the circuit. So where this comes about is that unless a load is purely resistive, there's more power is required than the average power dissipated by the device or that's used by the device. This is because the supply is going to have to provide not only the real power that will eventually be dissipated in a different form of mechanical heat energy, sound energy, some different type of form. But the supply also has to provide the power that is being absorbed within the system. And this apparent power is related to the power factor, which again is the cosine of the phase angle difference, by the following relationship. The power factor is also defined as the apparent power divided by defined by the real power, P, divided by the apparent power. So it's the rate at which useful energy, useful power that is changing electrical energy into another form of energy, it's the ratio between that and the amount of total power that has to be supplied to the system. So this is sort of an efficiency rating on our electrical transfer, our transfer of electrical energy from electrical form to some other form of energy. So in conclusion, here are the summary of all the complex power relationships. Again, complex power can be represented as a vector. And the reason we want to represent it as this complex vector is that we can calculate the complex power based on the product of the phasor RMS voltage and the phasor RMS current. Again, we know how to relate the RMS voltage to the peak or maximum voltage. The apparent power is the root mean squared of the complex power terms, of the real power and the reactive power. And it tells us about how much total energy must be, or the rate at which energy must be delivered to a system to deliver a specified amount of real or average power. Again, real power and reactive power are calculated by these relationships here. And the power factor tells us about the angular difference, the phase angle difference between the voltage and the current through an element, and is also related to the apparent power and the real power of the system.